So without any further ado, let's get started.
Now it's working. Cool. Thank you so much for this. Um, yeah, so originally the talk was about front-running hacks, but I figured to speak more broadly about hack prevention and what I think that everybody seems to missing. Um, yeah, so I'm a founder of Phylax. It's a new project in the area of hack prevention. I'm a technical advisor in a fund, and my villain origin story is from Nomad, where I was a protocol engineer, and I went through the hack. And being in the war room, talking with affected users afterwards, strategizing with the team was something very impactful. It was a formative experience. And it really made me understand that we have an issue in crypto with hacks. Um, Billions of dollars yearly are lost. And I think we need to create better solutions. And although it's good that we're talking about hack prevention, I feel that we are not viewing the problem from the right lens. So in this talk, I want to first define what's hack prevention, and then talk about the major design schools in hack prevention, which is front-running hacks, or what I call next block response, and why I think both of these solutions are not great. So let's take a very classic definition of incident response. We start with the surfacing of the issue. The hacker sends the malicious transaction in the mempool. That should trigger some alert. So now we know the hack is going on. We have detected it. And finally, we want to mitigate, right? We want to do something about it. And mitigation means return to normalcy. In Web 2, in DevOps, we define as mitigation the return to normalcy. We want to restore the issue before the user see that it's happening. And in blockchains, in order to return to normalcy, we have to not allow it to happen in the first place. Because in blockchains, as we know, once something happens, it's immutable. So, to be more specific, a DApp needs to be paused before the hack takes place. We need to prevent the hack from happening in the first place. The first large design school about hack prevention is front-running hacks. And it started in a very interesting way. As you may know, there's a lot of MEV searchers that create these generalizable bots that detect MEV opportunities and try to capture them. So a few years back, when a hacker would send a malicious transaction to the mempool, this generalized bot would detect the MEV opportunity and then copy it and essentially replace who will get the money from the hack with its own address. And then it would send this new transaction with higher gas. The proposer would read it from the mempool. I would emit a block. And the result would be that instead of the hacker getting the funds would be captured by these MEV bots. We have seen that in the wild. We have seen MEV searchers capturing hacks by mistake and then going through a process to return them to the dApps. So a few people figured out that since this is happening by accident, we should probably productize it, right? So the hacker will send a malicious transaction, the mempool, and then you have some software where it monitors the mempool. It would detect the malicious transaction and then send a mitigative transaction. So instead of front-running the hack with another hack, it will front-run the hack with a transaction that will pause the dApp. So when the proposer reads the mempool and executes the transactions in the same block, the hacker's transaction will be after the mitigative transaction, which means that the hack is resolved. The hack doesn't take place in the first place. And this is a quite good solution, right? Well, what if the hacker has access to a private mempool? What if the hacker sends the malicious transaction to this private mempool, and then the private mempool emits a block with a hack inside? At that point, there is no way for the front runner to actually see the transaction and front run it. This very simple solution actually makes all front running services useless. And I believe that in the future, as these front-running services become more and more apparent, the more and more dApps use them, we will see the creation of what I call the dark mempools, where there is a group of mempools, private and public, that collaborate with the services. They allow the services to observe their mempools, but there will be always a private mempool with proposers somewhere in some jurisdiction that doesn't cooperate, that will include your transaction, no questions asked. So at some point, a malicious transaction will be included in the block. So here, for example, we see that we have this cooperative, the good mempools, they produce the good blocks. And at some point, a proposer from the dark mempool will be elected as the next proposer and will emit a block with a hack. So maybe the hacker will need to wait more time to get their transaction included, but it will be included at some point. So front-running hacks depends on the hacker not using private mempools. In other words, it depends on the hacker being incompetent. In a world where front-running services become prevalent, hackers will just use private mempools, and immediately all these services will become quite useless. And an interesting thing we have to remember is that dark mempools are protocol compliant. They don't do anything illegal. They don't do anything wrong. Or more like, they do something illegal, but not from a protocol perspective. From a protocol perspective, they include valid transactions in valid blocks. So there is nothing really we can do at the protocol level. And based on the definition we gave for mitigation, front-running the hacks is mitigation, right? We stop the hack from taking place. We pause the dApp before the malicious transaction tries to do something about it. The next big design group, design school for hack prevention, is what I call next block response. It's very simple, really. First, the hacker will send their transaction. It will be included in a malicious in a block. Then the software will detect it and will send the mitigative transaction in the next block, right? Super simple. Much simpler than the front running of hacks we described. And this is useful for multi-block hacks, where for some reason the hacker needs to send transaction in multiple blocks. So the idea is that some part of the hack happens, you pause the dApp, and then the hacker can't do anything more about it. For example, with Euler, the hacker drained the pools one after the other in multiple blocks. But the problem is that there is no reason for the hacker to do so. The only reason that the hacker will not actually drain all the Euler pools in a single transaction, in a single block, is because they are incompetent. Again, it assumes that the hacker is not sophisticated, because a sophisticated hacker will be able to properly simulate the attack and execute it in a single block. So again, in a world where next block response becomes prevalent, it will become irrelevant, because the hacker will just perform more sophisticated hacks in a single block. And based on the definition we gave, next block response is not mitigation. It's damage control, right? Even if the hacker does the hack in multiple blocks, some part of the block will go through. We just hope that the hacker will not drain the whole pool in a single block, but will drain half of it. So, what to do? It's a cat and mouse, unfortunately. Both solutions work, but they have a time horizon, right? There is a near future where both of the solutions are no longer working because they force the hackers to become more sophisticated. I think we should build tools with the end in mind. which means that we should build tools assuming that the hackers are competent, that they are sophisticated, and then try to think what we can do in that end state. And I think the best design school is a new one where we don't allow the transactions and malicious transactions to land in the first place. And this is what we are exploring with Phylax, where essentially maybe the correct way to prevent hacks is to censor hacks. But we'll talk about that in another time. Thank you so much.